And this is going to use some of the techniques we learned last time with respect to amortized analysis. And what's neat about what we're going to talk about today is it's a way of comparing algorithms that are so-called online algorithms. And we're going to introduce this notion with a problem which is called self-organizing lists. Okay. And so the setup for this problem is that we have a list L of n elements. And we have an operation oops, got to spell things right. Access of x, which accesses item x in the list. Could be by searching, or it could be however you want to do it, but basically it goes and touches that element. And we're to say the cost of that operation is whatever the rank of x is in the list, which is just the distance of x from the head of the list. And the other thing that we can do is that the algorithm can do. So this is what the user would do. He just simply runs a whole bunch of accesses on the list, okay, accessing one element after another, okay, in any order that he or she cares to. And then L can be reordered, however, by transposing adjacent elements. And the cost for that is 1. So, for example, suppose the list is the following. Okay. I missed something here. Oh, it doesn't matter. I'll just make it be what I have so that it matches the online video. Okay, so here we have a list. And so if I do something like access element 14 here, the element with key 14, okay, then this costs me 1, 2, 3, 4. So here the cost is 4 to access. And so we're going to have some sequence of accesses that the user is going to do. And obviously, if something is accessed more frequently, we'd like to move it up to the front of the list so that you don't have to search as far. Okay? And to do that, if I want to transpose something, so for example, if I transpose 3 and 50, that just costs me 1. Okay? So then I would make this be 50 and make this be 3. Okay? Sorry, normally you just do it by swapping pointers. Okay? So those are the two operations. And we're going to do this in what's called an online fashion. So let's just define online. So a sequence S of operations is provided one at a time. For each operation, an online algorithm must execute the operation immediately. Without getting a chance to look at what else is coming in the sequence. So when you make your decision for the first element, you don't get to see ahead as to what the second or third or whatever is. Then the second one you get, and you have to make your decision as what to do, and so forth. So that's an online algorithm. Similarly, an offline algorithm, okay, may see all of S in advance. Okay, so you can see an offline algorithm gets to see the whole sequence and then decide what it wants to do about element 1, element 2, or whatever. Okay, so an offline algorithm can look at the whole sequence and say, okay, I can see that item number 17 is being accessed a lot. We'll move him early on, move him up closer to the front of the list, and then the accesses cost less for the offline algorithm. The online algorithm doesn't get to see any of that. Okay? So this is sort of like if you're familiar with the game Tetris. Okay? In Tetris, you know, you get one shape after another that starts coming down, and you have to twiddle it and move it aside and drop it into place. And there sometimes you get a one-step look ahead on some of them, so you can see what the next shape is, but often it's purely online. You don't get to see that next shape or whatever. And you have to make a decision for each one, and you make a decision, then you realize that the next shape's, if you'd made a different decision, it would have been better. Okay? So that's the kind of problem. Offline Tetris would be, I get to see the whole sequence of shapes, and now let me decide what I'm going to do with this one. Okay? Okay, and so in this, the goal for any of the algorithms, either online or offline, is to minimize the total cost, which will denote by, I forgot to name this. This is algorithm A here. Okay? The total cost C sub A of S. Okay, so the cost of algorithm A on the sequence S. That's just the notation we'll use for what the total cost is. So any questions about the setup for this problem? So we have an online problem. We're going to get these things one at a time. Okay, and we have to decide what to do. So let's do a worst case analysis for this. Okay, so if we're doing a worst-case analysis, we can view that we have an adversary that we're playing against who's going to provide the sequence. The user is going to be able to see what we do. And so what's the adversary strategy? What's that? Thwart our plots. Yes, that's his idea. And how is he going to thwart them? Or she? Which is what for this problem? What's he going to do?
Give us stuff again.
Yeah, no matter how we reorder elements using the transposes, he's going to look at every step and say, what's the last element? That's the one I'm going to access. Right? So the adversary always accesses the tail element of L, no matter what it is, no matter how we reorder things. Okay? For each one, adversary just accesses the tail. So the cost of this, of any algorithm then, is going to be omega size of s times n. Okay, because you're always going to pay for every sequence, you're going to have to go n, pay a cost of n, okay, for every element in the sequence. Okay, so not terribly in the worst case. Not terribly good. So people in studying this problem, question. That holds for the online algorithm, right. The offline algorithm, right, if you name those things, that's right. Okay? So we're looking at trying to solve this in an offline sense. In an online sense. Okay? And so the point is that for the online algorithm, the adversary can be incredibly mean. Okay? And just always access the thing at the end. Okay? So what sort of the history of this problem is that people said, well, if I can't do well in the worst case, maybe I should be looking at average case. Okay, and look at, say, the probability, the different elements having some probability distribution. Okay, so let's the average case analysis. Okay, let's suppose that element x is accessed with probability p of x. Okay, so suppose that we have some a priori distribution on the elements. Okay, then the expected cost of the algorithm on a sequence, okay, is, so this is if I put all of the elements into some order, okay, and don't try to reorder, but just simply look at, is there a static ordering that would work well for that distribution? It's just going to be, by definition of expectation, the probability of x times, in this case, the cost, which is the rank of x in whatever that ordering is that I decide I'm going to use. Okay? And this is minimized when? So this is just the definition of expectations. The probability that I access x times the cost summed over all the elements. And the cost is just going to be its position in the list. So when is this value, this summation, going to be minimized? When the element is most likely has the lowest rank, and then what? What about the other elements? Okay, so what does that mean?
So you order based on the probability of getting.
Yeah, so you sort them. Yeah, sort them on the base of decreasing probability. Okay? So it's minimized when L is sorted, okay, in decreasing order. With respect to P. Okay, so we'll just sort them with the most likely one at the front and then just decreasing probability. That way, whenever I access something with some probability, okay, I'm going to access, is more likely that I'm going to access. And that's not too difficult to actually prove. You just look at, suppose there were two that are out of order, and show that if you swap them, you would improve this, this optimization function. Okay? Okay, so if you didn't know it, this suggests the following heuristic. Okay, which is simply keep account of the number of times each element is accessed and maintain the list in order of decreasing count. Okay? So whenever something is accessed, increment its count. Okay? And that will move it at most one position, which only costs me one transpose to move it perhaps forward. Okay, actually, I guess it could be more if you have a whole bunch of ties, right? Yeah. So it could cost more. But the idea is over time, the law of large numbers says that this is going to approach the probability distribution. There's the frequency with which you access this divided by the total number of accesses will be the probability. And so therefore you'll get things sorted in decreasing probability. Okay, assuming that there is some distribution that all of these elements are chosen according to, or accessed according to. It doesn't seem like there's that much more you could really do here, and that's why I think this notion of competitive analysis is so persuasive, because it's really amazingly strong. Okay? And it came about because of what people were doing in practice. So in practice, what people implemented was a so-called move to front heuristic. Okay? And the basic idea was, after you access an element, just move it up to the front. Okay? That only doubles the cost of accessing the element, because I go and I access it, chasing down, paying the rank, and then I have to do rank number of transposes to bring it back to the front. So it only cost me a factor of 2, and now if it happens to be a frequently accessed element, over time you'd hope that the most likely elements were near the front of that list. So after accessing X, move X to the head of the list using transposes, and the cost is just equal to twice the rank in L of X, okay, where the 2 here has 2 parts. One is the access, and the other is the transposes. Okay? So that's sort of what they did. And one of the nice properties of this is that if it turns out that there's locality in the access pattern, if it's not just a static distribution, but rather once I've accessed something, if it's more likely I'm going to access it again, which tends to be the case for many input types of patterns, this responds well to locality, because it's going to be up near the front if I access it very soon after I've accessed it. So if there's what's called temporal locality, meaning that in time I tend to access things. So it may be that I access something that's very hot for a while, then it gets very cold. This type of algorithm responds very well to the hotness of the accessing. Okay, so it responds well to locality. In S. So this is sort of what was known up to the point that a very famous paper was written by Danny Slater and Bob Tarjan, where they took a totally different approach to looking at this kind of problem. Okay, and it's an approach that now you see everywhere, from analysis of caching in high-performance processors, to analyses of disk paging, to just a huge number of applications of this basic technique. And that's the technique of competitive analysis. Okay, so here's the definition. So online algorithm A is alpha competitive. Okay, if there exists a constant k such that for any sequence S of operations, the cost of S using algorithm A is bounded by alpha times the cost of of opt, where opt is the optimal offline algorithm. Okay? So the optimal offline, the one that knows the whole sequence and does the absolute best it could do on that sequence. Okay, that's this cost here. This is sometimes called God's algorithm. Okay, not to bring religion into the classroom or to offend anybody, but that is what people sometimes call it. Okay, so the fully omniscient knows absolutely the best thing that could be done, sees into the future, the whole works. Okay, gets to apply that. That's what opt's algorithm is. And what we're saying is that the cost is basically whatever this alpha factor is. It could be a function of things, or it could be a constant. Okay, times whatever the best algorithm is. Okay, plus there's a potential for a constant out here. Okay. So, for example, if alpha is 2, then we say it's too competitive. That means you're going to do, at worst, twice the algorithm that has all the information, but you're doing it online, for example. Okay? So really pretty powerful notion. And what's interesting about this is not even clear these things should exist, to my mind. Okay? What's pretty remarkable about this, I think, is that there's no assumption of distribution, of probability distribution or anything. It's whatever the sequence is that you give it, you're within a factor of alpha, essentially, of the best algorithm. Okay, which is pretty remarkable. Okay. And so we're going to prove the following theorem, which is the one that Slater and Tarjan proved. And that is that MTF is 4 competitive. For self-organizing lists. Okay? So the idea here is that suppose the adversary says, oh, I'm always going to access the thing at the end of the list, like we said in the beginning. Okay? So the adversary says, I'm always going to access the thing there. I'm going to make MTF work really bad because you're going to go and move that thing all the way up to the front, and then I'm just going to access the thing way at the end again. Okay? Well, it turns out that, yeah, that's a bad sequence for move to front. Okay? And it will take a long time, but it turns out God couldn't have done better. Okay? By more than a factor of 4. No matter how long the list is. Okay? That's pretty amazing. Okay? So yeah, that's a bad sequence. But if there's a way that the sequence exhibits any kind of locality or anything that can be taken advantage of, if you could see the whole thing, MTF takes advantage of it too. Okay, within a factor of 4. Okay, so really I think pretty remarkable theorem. Pretty remarkable theorem. And it's the basis of many types of online analysis of online algorithms. Almost all online algorithms today are analyzed using some kind of competitive analysis. Okay, not always. Sometimes you do probabilistic analysis or whatever, but the dominant thing is do competitive analysis, because then you don't have to make any statistical assumptions. Okay? Just prove that it works well no matter how. This is remarkable, I think. Isn't it remarkable? Okay. Okay. So let's prove this theorem. So we're going to spend the rest of the lecture on this proof. Okay? And the proof in some ways is not hard, but it's also not necessarily completely intuitive. So you will have to pay attention. Okay? Let's get some notation down. Let's let L sub I be MTF's list after the ith access. And let's let L be ops list after the ith access. Okay, so generally what I'll do is I'll put a star if we're talking about opt and have nothing if we're talking about MTF. Okay? So that's going to be the list. So we can say what's the list. So we're going to set it up as where we have an operation that transforms list I minus 1 into list I. Okay, that's what the ith operation does. Okay, and move to front does it by moving whatever the thing that was accessed to the front. And opt does whatever opt thinks is the best thing to do. We don't know. Okay? So we're going to let C sub I be MTF's cost for the ith operation. And that's just twice the rank in L sub I minus 1 of x if the operation accesses x. Okay, 2 times the rank in Li minus 1, because we're going to be accessing it in Li minus 1 and transforming it into Li. And similarly, we'll let C sub I star be ops cost for the ith operation. And that's just equal to, well, it's going to be, to access it, it's going to be the rank in Li minus 1 star, whatever its list is of x at that step, because it's got to access it. And then some number of transposes, Ti, if opt performs T sub I transposes. Okay? So we have the setup where we have 2 different lists that are being managed, and we have different costs in the lists. And what we're interested in is comparing in some way MTF's list with ops list at any point in time. And how do you think we're going to do that? What technique do you think we should use to compare these 2 lists? General technique. From last lecture. Well, it is going to be amortized, but what? How are we going to compare them? What technique did we learn last time for potential function? Good. Okay, we're going to define a potential function, okay, that measures how far apart these 2 lists are. Okay? And the idea is that if, so let's define that, and then we'll take a look at it. So we're going to define a potential function, potential phi mapping the set of MTF's lists into the real numbers by the following. Phi of Li is going to be twice the cardinality of this set. Okay, so this is the precedes operation in list I. So you can define a relationship between any two elements that says that x precedes L sub I, x precedes y in L sub I if as I'm accessing it from the head, I hit x first. Okay, so what I'm interested in here are, in some sense, the disagreements between the two lists. This is where x precedes y in MTF's list, but y precedes x in op's list. They disagree. Okay? And what we're interested in is the cardinality of the set, and we're going to multiply it by 2. Okay? So that's equal to 2 times, so there's a name for this type of thing. We saw that when we were doing sorting. Anybody remember the name? Briefly, very briefly. I don't expect anybody remembers it, but somebody might. Inversions, good. Okay, twice the number of inversions. So let's just do an example. So let's say L sub I is the list with 5 elements. Okay, let's say I'll use characters for the order, just to keep things simple. Okay, so in this case, phi of Li is going to be twice the cardinality of the set. So what we want to do is look to see which things are out of order. So here I look at E and C are in this order, but C and E in that order. So those are out of order. So that counts as one of my elements, EC. Okay? And then E and A and E. Okay, so those are out of order. And then ED, DE, out of order. And then EB, BE, those are out of order. And now I go CA, CA. Those are in order, so it doesn't count. CD, CD, CB, CB, so nothing with C. Then AD, AD, those are in order. AB, AB, those are in order. So then DB, BD, so BD. And that's the last one. So that's my potential function, which is equal to, therefore, 10. Because the cardinality of the set is 5. I have 5 inversions, okay, between the two lists. Okay? Okay, so let's just check some properties of this potential function. Okay? First one is that notice that phi of Li is greater than or equal to 0 for all I. The number of inversions might be 0, but it's never less than 0. Okay, it's always at least 0. So that's one of the properties that we normally have when we're dealing with potential functions. And the other thing is Well, what about phi of L0? Is that equal to 0? Well, it depends upon what list they start with. Okay? So, what's the initial ordering? So it's 0 if they start with the same list. Then there are no inversions. But they might start with different lists. We'll talk about different lists later on. But let's say for now that it's 0 because they start with the same list. That seems like a fair comparison. Okay. So we have this potential function now that's counting up how different are these two lists. And intuitively, what we're going to do is the more differences there are in the lists, the more we're going to be able to have stored up work that we can pay for. That's the basic idea. So the more that that opt changes the list so it's not the same as ours, in some sense, the more we're going to be in a position as MTF to take advantage of that difference in delivering up work for us to do. And we'll see how that plays out. So let's first also make another observation. So how much does phi change from one transpose? How much does phi change from one transpose? So basically, that's asking, if you do a transpose, what happens to the number of inversions? So what happens when a transpose is done? What's going to happen to phi? What's going to happen to the number of inversions?
Less than n minus 1?
So if I change, it is less than n minus 1, yes. If n is sufficiently large, yes. Okay? But if I change, so you can think about it here. Suppose I switch two of these elements here. How much are things going to change? Yeah, it's basically 1 or minus 1. Okay? Because a transpose creates or destroys one inversion. So if you think about it, if I change, for example, C and A, the relationship of C and A to everything else in the list is going to stay the same. The only thing possibly that happens is that if they're in the same order when I transpose them, I've created an inversion. Or if they were in the wrong order when I transpose them, now they're in the right order. So therefore, the change to the potential function is going to be plus or minus 2 because we're counting twice the number of inversions. Okay? Any questions about that? So transposes don't change the potential very much. Just by 1. It either goes up 1, goes up by 2, or down by 2. Just by 1 inversion. So now let's take a look at how these two algorithms operate. Ugh. Okay, so what happens when op_i accesses x in the two lists? What's going to be going on? So to do that, let's define the following sets. Okay. So we're going to look at when we access X, we're going to look at the two lists and see what the relationship is. So let me, based on things that come before and after. So I think a picture is very helpful to understand what's going on here. Okay, so so here's L sub I minus 1, and we have our list, which I'll draw like this, and somewhere in there we have X. Okay, and then we have L sub I minus 1 star, which is ops list. Okay, and he's got X somewhere else, or she. Okay. And so, what is this set? This is the set of Y, okay, that come before X. So that's basically sets A and B. Okay, those things that come before X in both. And some of them, the A's, come before it in X, but come after it in come before it in A, but come after it in B. Okay, and similarly down here, what's this set? That's A union C. Good. And this one? Duh. Yeah, C, it better be C union D, because I got A union B over there, and I got X, so that better be everything else. Okay, and here is B union D. Okay? So those are the four sets that we're going to care about. We're actually mostly going to care about these two sets. Okay? And we also know something about the R here. The position of X is going to be the rank in L minus 1, L sub I minus 1 of X. And here, this is R star, is just the rank in L sub I minus 1 star of X. So we know what these ranks are. And what we're going to be interested in is in fact, what the characterizing the rank in terms of the sets. Okay, so what's the position of this? Well, the rank, we have that R is equal to the size of A plus the size of B plus 1. Okay, and R star is equal to the size of A plus the size of C plus 1. So let's take a look at what happens when these two algorithms do their thing. So when the access to X occurs, we move X to the front of the list. Okay, goes right up to the front. So how many inversions are created and destroyed? So how many are created by this? That's probably a... How many inversions are created? How many inversions are created? So we move X to the front. So what we're concerned about is that anything that was in one of these sets that came where it's going to change in order versus down here. So if I look at B, well, let's take a look at A. Okay, So A, those are the things that are in the same order in both. So everything that's in A, when I move x to the front, each thing in A is going to count for one more inversion. Does everybody see that? So I create the cardinality of A inversions. And we're going to destroy, well, everything in B came before x in this list and after x in this. But after we move x, they're in the right order. So I'm going to destroy B inversions, order B, cardinality of B inversions. Okay? So that's what happens when we operate with move to front. We create A inversions and destroy B inversions. Okay, by doing this movement. Okay. Now, let's take a look at what opt does. So each transpose, we don't know what opt does. He might move x this way or that way. We don't know. But each transpose by opt, well, we're going to be interested in how many inversions it creates, and we've already argued that it's going to create at most one inversion per transpose. So he can go and create more inversions. Okay? So let me write it over here. Thus, the change in potential, the change in potential is going to be at most twice A minus B plus Ti. Okay, so Ti, remember, was the number of transposes that opt does on the ith step for the ith operation. Okay? So we're going to create the change in potential is at most twice this function. So we're now going to look to see how we use this fact and these two facts, this fact and this fact, okay, to show that opt can't be much better than MTF. Okay. Good. The way we're going to do that is look at the amortized cost of the ith operation. Okay, what's MTF's amortized cost? Okay, and then we'll make the argument, which is the one you always make, that the amortized costs upper bound the true costs. Okay, but the amortized cost is going to be easier to calculate. Okay, so amortized cost is just C hat. Actually, let me make sure I have lots of room here on the right. C sub I hat, which is equal to the true cost plus the change in potential. Okay, that's just definition of amortized cost when given potential functions. Okay? So, what is the cost of operation I? Okay, in this context here. Okay, we accessed x there. What's the cost of operation I? 2 times the rank of x, which is 2r. Okay, so 2r for that part of it. Okay, plus, well, we have an upper bound on the change in potential. That's this. Okay, so that's 2 times cardinality of A minus cardinality of B plus T sub I. Okay, everybody with me? Yeah, okay, I see lots of nods, that's good. Okay, that's equal to 2r plus 2 of size of A minus, okay, I want to plug in for B. And it turns out very nicely, I have an equation involving A, B, and R. So I get rid of the variable size of B by just plugging that in. Okay? And so what do I plug in here? What's B equal to? Yeah, R minus size of A minus 1. I wrote it the other way. Okay? And then plus Ti. Okay, and this is since R is A plus B plus 1. Okay, everybody with me still? Just doing algebra, but we've got to make sure we do the algebra right. Okay, so that's equal to, let's just multiply all this out now. We get 2r plus, I have 2a here minus a, so that's 4a. And then 2 times minus r is minus 2r. 2 times minus 1 is minus 2. Oh, but it's minus minus 2, so it's plus 2. Okay. And then I have 2ti. So that's just algebra. Okay. So that's not bad. We've just gotten rid of another variable. What variable did we get rid of? R. Didn't matter what the rank was as long as I knew what the number of inversions was here. Okay? So that's now equal to 4a plus 2 plus 2ti. And that's less than or equal to, I claim, 4 times r star plus ti, using our other fact. Since r star is equal to the size of A plus the size of C plus 1, and that's greater than or equal to the size of A plus 1. Okay, so if I look at this, I'm basically looking at A, the fact that that A, what did I do here? So we have r star is greater than or equal to A plus 1, right? So therefore, A plus 1, good. Yeah, so this is basically less than or equal to 4a plus 4, which is 4 times a plus 1. Probably should have put in another algebra step here, okay? Because if I can't verify it like this, then I get nervous, okay? But this is basically at most 4a plus 4. That's 4 times a plus 1, and a plus 1 is less than or equal to r star. And then 2ti is at most 4ti. So I've got this. Okay, does everybody see where that came from? But what is r star plus ti? What is R star plus Ti? What is it? It's Ci star. That's just Ci star. So the amortized cost of the ith operation is at most 4 times ops cost. Okay? That's pretty remarkable. Okay? So the amortized cost of the ith operation is just 4 times ops cost. Now, of course, we have to now go through and analyze the total cost. But this is now the routine way that we analyze things with potential functions. So the costs of MTF of S is just the summation of the individual costs. Okay, by definition. And that is just the sum I equals 1 to S of the amortized cost plus the minus the change in potential. Okay. Did I do this right? No, I put the parentheses in the wrong place. No, now I've got it right. Good. I just missed a parenthesis. Okay. So this is, in the past what I did was I expressed the amortized cost as being equal to Ci plus the change of potential. I'm just throwing these two terms over to the other side and saying what's the true cost in terms of the amortized cost. Okay, so I get phi minus 1 plus phi sub li at minus 1 minus phi of li. Okay, by making that substitution. Okay, that's less than or equal to, since this is linear, well, I know what the sum of the amortized cost is. It's at most 4 Ci star. So the sum of them is at most, so that's sum I equals 1 to S of 4 Ci star. And then, as happens in all these things, you get a telescope with these terms. Every term is added in once and subtracted out once, except for the ones at the limit. So I get plus phi of L0 minus phi of L subcardinality of S. And now this term is 0. And this term is greater than or equal to 0. Okay? So therefore, this whole thing is less than or equal to, well, what's that? That's just 4 times ops cost. And so we're 4 competitive. Okay? This is amazing, I think. Okay, it's not that hard, okay, but it's quite amazing that just by doing this simple heuristic, you're nearly as good as any omniscient algorithm could possibly be. Okay, you're nearly as good. And in fact, in practice, this is a great heuristic. So if ever you have things like a hash table that you're accessing by chaining, okay, often it's the case that if when you access the elements, you just bring them up to the front of the list. If it's an unsorted list that you've put them into, just bring them up to the front. You can easily save 30–40% in runtime for the accessing to the hash table, because you'll be much more likely to find the elements inside. Of course, it depends on the distribution and so forth, and for empirical matters. But the point is that you're not going to be too far off from the ordering that an optimal algorithm would do. Optimal offline algorithm. I mean, amazing. Okay, optimal offline. Now, it turns out that in the reading that we assigned, so we assigned you Slater and Tarjan's original paper. In that reading, they actually have a slightly different model where they count transposes that move an accessed element X toward the front of the list as free. Okay? So, and this basically models, so basically here's the idea, is if I actually have a linked list, then when I chase down, once I find X, I can actually move X up to the front with just a constant number of pointer operations to splice it out and put it up to the front. I don't actually have to transpose all the way back down. Okay? So that's kind of the model that they use, which is a more realistic model. Okay? I presented this argument because it's a little bit simpler. Okay? And the model's a little bit simpler. But in their model, they have, if when you access something, you want to bring it up to the front, or anything that you happen to go across during that time, you can bring up to the front essentially for free. The model, this model is the splicing in, splicing X in and out of L in constant time. Then MTF is, it turns out, too competitive. It's within a factor of 2 of optimal. Okay, if you use that. And that's actually a good exercise to work through. You can also go read about it in the reading. But to understand this better, look to see where you would use those things. You have to have another term representing the number of, quote, free transposes. But it turns out that all the math works out pretty much the same. Okay. Let's see. Another thing I promised you is what if, to look at the case, what if they don't start with the same list? Okay. What if the two lists are different when they start? Then the potential function at the beginning might be as big as what? How big could the potential function start out as if the lists are different? So suppose that we're starting out, you have a list, and op says, okay, I'm going to start out by ordering my list according to the sequence that I want to use. Okay, and MTF orders it according to the sequence it wants to use. What list is opt going to start out with as an adversary? Yeah, he's going to pick the reverse of whatever MTF starts out with, right? Because then, and if he picks the reverse, what's the number of inversions? It's how many inversions in a reverse ordered list? Yeah. N choose 2. Okay. Is it n choose 2 or n minus 1 choose 2? N minus 1 choose 2. Okay. Inversions that you get, because basically it's triangular number. okay, when you add them up. But in any case, it's order n squared. Worst case. So what does that do to our analysis here? It says the cost of MTF of S is going to be, well, this is no longer 0. This is now n squared. Okay, so we get that the cost of MTF of S is at most 4 times ops thing plus order n squared. Okay? And if we look at the definition, did we erase it already? Erase the definition of competitive. Okay? This is still for competitive. Okay? Since n squared is constant as the size of S goes to infinity. This is once again sort of your notion of what does it mean to be a constant. Okay? So as the size of the list gets bigger, all we're doing is accessing whatever that number n is of elements. That number doesn't grow with the problem size. Okay, even if it starts out as some variable number n. Okay, it doesn't grow with the problem size. We still end up being competitive. This is just the k that was in that definition of competitiveness. Okay. Any questions? Yeah.
How can you say that it takes exactly as long to traverse an element of the list as the next list?
Well, you could change the cost model a little bit.
Number 4 depend on that?
Yeah. Yep. And that's a good one to work out. What if you say the cost of transposing? So cost of transposing is probably moving 2 pointers, approximately 3 pointers. So suppose that the cost of, wow, that's a good exercise, okay? Suppose the cost was 3 times to do a transpose, was 3 times the cost of doing an access, following a pointer. Okay, how would that change the number here? Okay, good exercise. Great exercise. Okay, good final question. Okay, yes, it'll affect the constant here. Just as when we do the free transpose, when we move things towards the front, that we consider those as free. Okay, those operations end up reducing this constant as well. Okay, but the point is that this constant is independent of the constant having to do with the number of elements in the list. So that's a different constant. Okay, so this is a constant. Okay. And so as with a lot of these things, there's 2 things. One is there's the theory. So theory here backs up practice. Okay, those practitioners knew what they were doing. Okay, without knowing what they were doing. Okay, so that's really good. Okay, and we have a deeper understanding that's led to, as I say, many algorithms for things like, the important ones are like paging. So what's the common page replacement policy that people study? People have in most operating systems. Who's done 6033 or something? Yeah, it's least recently used, LRU. People have heard of that. Okay? So you can analyze LRU competitive and show that LRU is actually competitive. Okay, with optimal page replacement under certain assumptions. Okay? And there are also other things, like people do random replacement algorithms, and there are a whole bunch of other kinds of things that can be analyzed with the competitive analysis framework. Okay? So it's very cool stuff. And we're going to see more in recitation on Friday. We'll see a couple of other really good problems that are maybe a little bit easier than this one. Okay? Definitely easier than this one. Okay? They give you hopefully some more intuition about competitive analysis. I also want to warn you about next week's problem set. Okay. So next week's problem set has a programming assignment on it. Okay? And the programming assignment is mandatory. Okay? Meaning, well, all the problem sets are mandatory, as you know, but if you decide not to do a problem, there's a little bit of a penalty, and then the penalties scale dramatically as you stop doing problem sets. But this one is mandatory. Okay? You don't pass the class. You get an incomplete if you do not do this programming assignment. Now, I know that some people are less practiced with programming. And so what I encourage you to do over the weekend is spend a few minutes and work on your programming skills if you're not up to snuff in programming. It's not going to be a long assignment, but if you don't know how to read a file and write out a file and be able to write a dozen lines of code, okay, if you're weak on that, this weekend would be a good idea to practice reading in a text file. It's going to be a text file. Read in a text file, do some manipulations, write out a text file. Okay? So I don't want people to get caught with this being mandatory and then not have time to finish it because they're busy trying to do trying to learn how to program in short order. I know some people take this course without quite getting all the programming prerequisites. Here's where you need it. Question? No language limitations. Pick your language. Okay, the answer will be written, I think, in Java, and Eric has graciously volunteered to use Python, okay, as for his solution to this problem. We'll see whether he'll live up to that promise. I hope I'm not. You did already, okay. And George wrote the Java solution. And so C is fine. MATLAB is fine. Okay, I don't know if, what else is fine? Anything's fine. Scheme is fine. Scheme is fine. Scheme is great. Okay? So any such things will be just fine. Okay? So we don't care what language you program in, but you will have to do programming to solve this problem. Okay? So thanks very much. See you next week.